Hey, we're back. Welcome back to EE282. There are no new handouts this time. There'll be some more handouts coming on Tuesday. There were 4 handouts last Tuesday. And if you didn't get any of them, go to ERL 444. These are posted. Okay. Well, it looks like we have some new information. This will also be on a handout for next time. We have office hours for the TAs as follows. Monday from 11 a.m. to 12:30, Lance Hammond in ERL 111. Monday, 7 p.m. to 9 p.m., David Heine, ERL 127. Tuesday in the evening, 6 p.m. to 8:30, Lance again, ERL 111. Wednesday in the afternoon and the evening, 1 p.m. to 3 p.m., 6 p.m. to 8 p.m., David and Albert. And if you're trying to get into the ERL building after 5 o'clock, the handle is locked, the door is locked. In order to get in, you need to use the front door combination, which is that. Don't tell anyone who might steal something. And this week only, special, one time, Friday 10 to 12, ERL 127. Who's going to be doing that? David. David's going to be doing that. I'll put these in an updated version of the introductory handout number 1 and send it out.
Also, all of this is put online in the news group.
Yes, all that information is also online in the news group. Review sessions will be held weekly on Friday mornings, beginning next week. In this building, but the room upstairs, Skilling 193, 11 o'clock. And the first one will be on an introduction to Verilog. It will be televised on the same channel, Friday 11 o'clock live, so people in SITN can listen in to the review sessions. Any questions on administrative issues or anything else? Okay, thank you for that. When last we left our ace computer designer on Tuesday, he or she had just discovered 2 kinds of locality of memory address references that can be used to make machines go faster. One is spatial locality, which is that if you reference location I, chances are pretty soon later you're going to reference location I plus 1 or I minus 1 or something fairly close. The other is temporal locality, which is that if you've referenced location I, chances are that sometime in the near future you're going to be referencing location I again. And you can use that to fake something that we would like that we can't have, which is very big, very cheap, fast memories. And what we do have are small memories that are reasonably inexpensive but have very short access time. And the reason why that's true is that for smaller memories, there are fewer address bits. You have to put less hardware into doing the decoding, so the decoding can be done faster. You can afford to take more space for a bit, so you can put more transistors into the bit. You can not have them be capacitively charged kind of dynamic RAMs, but you can have them be active flip-flops and switch more quickly. And therefore, they're geographically less dense. There are few of them that you can put in a square micron of space. But fast memories cost an awful lot. So the obvious win is to take a fast memory, put the common references into that fast memory, put the less common references into the slow memory, and get something which is almost as fast as the fast memory, but costs almost as little as the large memory. At least that's the objective. And I'm sure you've all seen caches before. All references are directed to the cache, which is small, fast, and expensive. If the information you happen to be looking for is in there, then you get it quickly. If not, then those few references that are not in the cache go to some slower memory. And of course, you can almost infinitely elaborate this. This main memory could in fact be a cache for some even bigger and slower memory. Let's make sure that we can do the kind of back-of-the-envelope performance calculations that we've been talking about for those kinds of memory hierarchies. let's say we have, which is quite common these days, a three-level cache hierarchy. If we have, for example, a CPU, and that CPU happens to have a cache embedded on it, the next level cache after that might be a slightly larger, slightly slower, slightly more expensive second level cache. And if the information isn't in the second level cache, then there is eventually the large main memory, which is even slower but much larger. Now, of course, there can be a third level here, and often is for virtual memory paging off to the disk, but we won't consider that at the moment. So how does one go about calculating, in fact, with this assembly of memories and caches, how fast on the average a given access is? Well, let's say that for this cache, 90% of the references are hits. When the CPU makes a request, 90% of the time the value is found in that memory. And let's say that when that happens, it takes one cycle. Something like that. If it's not found there, then it goes to the second level cache. And let's say that 9% of the time that happens, and that it takes 10 cycles to go to that cache memory. And the fallback position, the remaining 1% of the time, it goes to main memory, and it takes 100 cycles. So the question is, and it's fairly trivial to calculate, what's the average memory access time? Often abbreviated AMAT. Well, 90% of the time, or 0.9% of the time, it's one cycle. 9% of the time, or 0.09, it's 10 cycles. That was a multiplication. And the remaining 1% of the time, it's 100 cycles. So it's 0.9 plus 0.9 plus 1, making 2.8 cycles. So the average amount of time that an access to the CPU will be charged for making a memory reference is 2.8 cycles. That's closer to 1 than 100. Obviously, you've gained an awful lot. It's not as perfect as a memory as big as you would like, all made out of the high-speed cache, but of course you can't have that. Any questions on computing average memory access times? Pretty straightforward. Go over a couple of things fairly quickly, back to philosophical considerations of how to make designs last for a long time. As an architect, you wind up designing both instruction set architectures and implementations that last over several generations of technology. And let's take a look at how quickly that technology increases in various areas. One of the problems is that they're not all increasing at the same rate. IC logic is increasing in density at about 40% per year and in speed about 25% per year, which is pretty impressive. But DRAMs are increasing in density about 60% a year. So they're going up in density about 4 times every 3 years. And in fact, they tend to go up in steps of 4 rather than steps of 2 or any other number. The problem is that their speed increase is much lower. So the gradual gap between the IC logic speed, which is the speed at which the processor runs, and the speed at which memory accesses are made is increasing. And this is what leads one to investigate even more and faster and higher level caches in order to be able to compensate for the fact that the processor is getting fast faster than the memory is getting fast. Disks have sort of the same problem, that they're increasing in density at a reasonably fast clip, but they're not increasing in speed as quickly. So as part of the memory hierarchy, you need to include disk and have the same kinds of caching mechanisms to cover up for the fact that they're not getting as fast as quickly. Another column, actually, that would be interesting to add to this is the cost decreases per year, and to chart those as well. DRAM and disk costs are coming down at incredible rates, and CPU costs are not coming down quite so quickly. In addition to hardware trends, there are software trends that you need to keep in mind. And the single most important one, which you'll learn to appreciate, or if you haven't already, is the voracious appetite that applications have for memory. It's going up, the amount of memory that applications use, by about 50% to 100% per year, which means that every additional year you need an extra half to 1 address bits. In fact, Gordon Bell, I guess, proposed a formula at one time for the number of bits that a state-of-the-art computer at any given year might need, and that formula is 2 to the t minus 1962, where t is the current year. And if you look at that over time, it actually tracks fairly well. We're at about 94, 95, so we're at 2 to the 32 bits, which is 2 to the 29th bytes, which is about 100 megabytes, and that's about right. And the state-of-the-art computers that you buy these days is about 100 megabytes. So in fact, it's been tracking 100% per year for a long time. And the single most important mistake that computer designers can make and have made consistently over the years is simply not including in the design of their computers enough address bits to accommodate the lifetime of the computer. The other software trend is that high-level languages are being used instead of machine languages, and that there's a close interaction between the compilers and the architecture. There's also a close interaction these days between compilers and implementation. To get the highest speed out of the current processors, the compilers need to know not only about the architecture, the design of the instruction set, but also about the implementation techniques to do some of the things we'll see later, instruction reordering and renaming, in order to get the highest performance. So these are the things that you need to think about in designing computer architectures to make sure that the design scales with advances during the lifetime of the computer. And the computer will last probably a long time. An architecture like the IBM 360 has lasted now for 30 years and is still going strong. It just barely provided enough address bits. When it first came out, it had provided 24 bits. The designers had thought of a way to extend it to 32 bits, and in fact, it eventually was extended to 32 bits. But in the meantime, the software engineers had discovered a way to use the extra 8 bits, and in fact, in a lot of the operating system software code for original 360s, those 8 bits were used for other things, flags and whatnot. So when the eventual transition to 32 bits occurred, it was a very painful process. In the design of some of the current RISC chips with 32 bits of address, they, I think, were a bit more clever in expecting that the next generation would go to 64 bits and tried to plan for it in such a way that even the software designers couldn't thwart their effort to get to 64 bits. We've talked about these things before, closing the speed gap between processor and DRAM, and closing the gap between the fact that DRAMs are getting denser but not faster at the same rate. The other thing is to realize that design of computers take a while, and if you're starting to design a computer now and it's going to take 2 years to get out, then the competition at that point will be 2 years ahead of the computers that exist now. So you've got to plan for future competition, not current competition. One way to deal with that is shorten the design cycle, but that's not easy to do. We're always looking for kind of rules of thumb that guide us in the design of computers, and we've been talking about several of them, but another one that Amdahl and Case came up with a number of years ago that seems to pass the test of time is that for any given computer, if you're going to provide n MIPS, millions of instructions per second, which is a fairly bogus number, we'll see later, but is sometimes useful. If you're going to provide a computer that runs at n MIPS, you're probably going to need to provide n megabytes worth of memory to go along with it to have the machine design be balanced, and probably going to need to provide n megabits per second of I/O. Now, as most rules of thumb, this depends a lot on the particular circumstances, and this will change depending on the application. If you're building a communications processor, obviously you're going to want to put more emphasis on the megabits per second of I/O and perhaps less emphasis on the total amount of memory. But This, again, seems about right for current workstation class machines. If it's a 100 MIPS machine, you probably want to give it 100 megabytes of main memory, and probably 100 megabits per second of I/O is about right. The other thing, real quickly, is that if you're given the task of designing a computer, you can't do that unless you know what the cost and performance targets are. And there are wide extremes. There are some designs where cost is really not an issue, and your object is to build the fastest possible high-performance, low-volume computer you can, like the kind of computers that Seymour Cray used to and still does design. It used to be a joke that the standard price for a Seymour Cray machine was $6 million. Every generation he would produce a new machine, and every generation the price would be $6 million. And he would have a standard list of customers that he could sell to, like Livermore Labs and other government-funded organizations. It's getting harder and harder to design machines that people are willing to spend $6 million for. So, in fact, he's and the other supercomputer manufacturers are in a bit of a squeeze. At the other end are the low-cost, high-volume computers, which go into video games and Nintendo gadgets and whatnot. And there the trade-offs are very much different, and every 10 cents that you can save on the cost is a major issue in the design of the computer. In some ways, these are the easy ones to do because you know exactly what the targets are. The hardest ones to do are the ones where the cost and performance are balanced, like the current workstations. And there you have to be the most careful in deciding what your trade-off is going to be, or what your company's trade-off is going to be between cost and performance. It's interesting that the VLSI processors are closing the gap between the low end and the high end, or at least between the medium end and the high end, that even now some of the fastest supercomputers are starting to be built out of the same processors that the workstations are being built out of, and they get their advantage from clever ways to assemble them in groups rather than high-speed execution units that are unique to those computers the way they did in the old days. Enough philosophy. We're analyzing machines based on cost and performance. Let's talk a bit about how it is that one measures performance. And the claim is, in fact, there are lots of measures, but the only valid measure of how good a computer is how long it takes to execute the problem that you have to execute. The execution time for a particular program, where the particular program is the one that your customer wants to run and is willing to pay you money for your computer for. But even that is a bit problematical because execution time can be composed of several different components. One is the wall clock time. You stick your job in the computer, you start it up, and you wait for it to finish, and when it's done, you click the stopwatch, and that's how long it took. The problem is that includes lots of things, including the time it took to do disk and other I/O, operating system overhead, competition with other jobs. It's difficult to extract from that the contribution of the various factors. So one of the first simplifications is to say, well, we're only going to look at CPU time. We're going to look at the processor time for a particular job. We're going to exclude I/O. In fact, you may or may not want to include operating system CPU time, depending on what the focus of the study is. If you exclude operating system CPU time, then you're looking at only user CPU time, which is a lot of the measurements we'll be looking at. And you're concentrating there primarily on the user state execution rate of the processor. Okay, so we have CPU time. Let's say that we're concentrating on the user state execution time of the CPU. How is it that we can divide that into units that seem meaningful to us? Well, one unit to divide it into are the instructions that are being executed. During the execution of the program, instructions are executed every so often. That's one division that we can make. Another division that we can make is that internally to the CPU there are clock cycles that may be going on that subdivide the execution of an instruction into smaller units. the sum of the execution of the program represents the sum of all of the cycles that compose all of the instructions. So the total CPU time is the CPU clock cycles for the entire program times the clock cycle time. And one of the things that's useful to measure is the number of cycles per instruction, and we'll be focusing on this a lot in order to look at the effectiveness of the performance increase of various computers. So the number of cycles per instruction is just the CPU clock cycles for the entire program divided by the instruction count, the average number of cycles per program. So now the CPU time is the product of three factors. The instruction count, which is the instructions per program, times the cycles per instruction, which is the cycles divided by the number of instructions in the program, times the clock cycle time, which is the number of seconds per cycle. And it's handy often to do this kind of dimensional analysis just to see that you're not adding apples and oranges. Cancel instructions and cycles, and in fact this is the number of seconds per program, which is the CPU time. In fact, a lot of the even more complicated problems that we'll be going over, it's handy to double check yourself at least by doing this kind of unit analysis to make sure things are working right. You got to be a little careful though. I remember one guy showing me that in fact the way to demonstrate that 16 over 64 is equal to 1 over 4 is simply to cancel the sixes. So you've got a little, you can go wrong by doing dimensional analysis, but at least you know that it's, if the dimensional analysis is wrong, the answer is wrong. If the dimensional analysis is right, the answer is not necessarily right. But showing the CPU time in this way gives us a handle on understanding what it is that changes in, that the changes in various parts of the computer, what effect they will have on the various components of the CPU time. The compiler is sort of the only pure play, as stockbrokers like to say. The increases in the technology of the compiler will decrease the number of instructions per program and probably always decrease the CPU time. Obviously, if it doesn't do that, you shouldn't use the new version of the compiler. Unfortunately, lots of the other changes in other components of the architecture have dual effects. The instruction set architecture, for example, if you change the instructions so that you need fewer instructions per program, sounds like a good thing, but the side effect of that often is that the number of cycles per instruction will go up. If you change the organization of the computer internally so that the number of cycles per instruction goes down, then in fact each cycle may be doing more, so the number of seconds per clock cycle may be going up. So a lot of these, including the technology, are maybe trade-offs, and increasing one of the factors will decrease the other factor. The thing we'll see is that you've got to be very careful to focus on the total CPU time as the measure of the performance of the CPU and not any individual one of these things, because otherwise you'll be increasing it to the detriment of one of the others. Let's elaborate that a little more. We know that there are lots of different kinds of instructions, and we might be interested in focusing on those different instructions and understanding each of their contributions to the performance of the computer. So let's say now that CPU time is again the total number of cycles, but now we're going to break that down into the number of cycles per instruction of instruction type I times the number of instructions of type I that were executed. This again is the total number of cycles times the clock cycle time, so it's the total CPU time. But now the average cycles per instruction is the weighted average of the cycles per instruction for each of the individual instructions times the frequency that that instruction is executed, which is the count of the number of times that instruction is executed divided by the total number of instructions in the program. Pretty straightforward, but we'll use this kind of calculation a fair bit to analyze the effect of changing various instructions. So in fact, let's do one of those. Let's say that we have a CPU, which is a RISC-like processor. It's a simple load store machine, and we've only got 4 different kinds of instructions. We've got loads, stores, branches, and ALU instructions. And we've measured on the benchmark that we're interested in the frequency of occurrence of each of these instructions as 25%, 15%, 20%, and 40%. And we know from the design of the machine that all of the instructions take 2 cycles except for the ALU instruction, which only takes a single cycle. Now let's look at the possible improvement of this machine by changing the semantics of one of the instructions. Right now, let's say that we have conditional branches that only test against 0. So the only 2 instructions there are that do conditional branches are a branch if equal to 0 based on a test of register n to some location, or a branch if not equal to 0 based on a test of register n to some location. Now it turns out that we often wind up doing compares followed by branches. So we might do a compare instruction that compares and puts into register 3 the result of comparing R1 and R2, and then branch based on whether or not R3 is 0 or 1. If that sequence is done very frequently, it might be an interesting thing to combine a single instruction, which is a complex branch, that allows us to do in a single instruction branch if equal register 1, register 2, loc. The question is that worthwhile? Well, we need some additional information. Let's assume that of all of the branches that the program ever executes, 25% of them will use this complex scheme. And what that means is that all of the branches will still be there, but if we use the complex scheme, we get to remove the preceding compare instruction. So that for 25% of the branches, the preceding compare instruction disappears. The question is, should we do it? Now, if you've given no other information and you know that the new machine will run just as fast in cycle time as the old machine, then the answer clearly is yes, because you remove some instructions, they all run at the same rate. Just to make the problem more interesting, let's say that the cost of adding this additional complex instruction is that you have to increase the cycle time of the new machine by 10%. Now it's not so clear whether it's a win or not. So let's go through the numbers and see if we can predict it. We need to compute the average number of cycles per instruction on the existing machine first. So we know that 25% of the instructions were loads, and they were 2 cycles, and that's this component. We know that 15% of the instructions were stores, and they took 2 cycles, that's this component. We know that 20% were branches, and they were 2 cycle instructions. And 40% that remained were ALU operations, and they were 1 cycle. Simple weighted average, 1.6 cycles per instruction. So the CPU time for running any particular program is going to be 1.6 times the instruction count of the particular program, whatever it is, we don't care, times the cycle time of the original machine. Now let's do the same calculation for the new machine. We haven't affected any of the loads. They're still there. 25% take 2 cycles. We haven't affected the stores. They're still there. 15% take 2 cycles. Remember that we're not removing any of the branches. We're making some of them more complicated, but they're still there. So the 20% of the branches taking 2 cycles are still there. What we have affected are the ALU instructions. Of the 40% of ALU instructions that used to be there, we said that 25%, those that correspond to 25% of the branches will disappear. So there are 20% of the instruction that are branches. Of those branches, 25% of them represent ALU instructions that are going to be disappearing. So now the number of ALU instructions is 0.4 minus 25% of 0.2, and ALU instructions still take 1 cycle. That's the number of cycles. We now have to divide by the number of instructions, and since we've removed those ALU instructions, instead of dividing by 1, we need to divide by 1 minus 25% of 20%, representing the ALU instructions that disappeared. So the new number of cycles per instruction is 1.63 instead of 1.6. Now the new instruction count, in fact we just went through that calculation, this is 1 minus 0.05 or 0.95. The new instruction count is 0.95 times the old instruction count. And we were told that the new cycle time of the machine is 10% longer than the old cycle time, 1.1 times the old cycle time. So now we can multiply those factors together, the new instruction count, the new cycles per instruction, and the new cycle time, and determine whether the new machine is better or worse than the old machine. In fact, the answer is that the new CPU time is 1.71 times the old instruction count and the old cycle time. The old CPU time was 1.6 times the old instruction count and the old cycle time. So the answer is, don't do it. It's not a worthwhile performance increase. Do you follow that? Any questions? Now it turns out that you may have noticed that we're doing something that looks a little silly, because we're dividing by 0.95 to produce the new cycles per instruction, and then wind up multiplying by 0.95 to produce the new instruction count. Is there a way to do that that avoids doing that extra work? And in fact, there is, if you don't really care to know what the new number of cycles per instruction is. Now, as before, the old CPU time is 1.6 times the old instruction count times the old cycles per the old cycle time. Now let's say that one way to think about this is that those ALU instructions that we're making disappear, in fact, don't disappear, they just take 0 time. And we might imagine that we're executing the same number of instructions, and some of them take 0 time. So if we calculate the new number of cycles per old number of instructions, we get the same first 3 components. We get the same last component, and then there's a hidden component here, which is the 0.25 times 0.2 times 0, representing the ALU instructions which are still there and take no time. So now the new CPU time is the new cycles per old instructions times the old number of instructions times the new cycle time. So it's 1.55 times the old instruction count times 1.1 times the old cycle time. Same answer. You avoid having to, in fact, calculate the new cycles per instruction. Any questions? Now, it is in fact the case that looking at the execution time on a particular program is the only good way to measure the performance of the computer. The problem is people don't like to do it, and there have been lots of uses of other numbers to measure the performance of computers. Why don't people want to use execution time? Well, because it leads to embarrassing questions. If you say that this computer is 10 seconds fast, you have to answer the question about 10 seconds on what? What program? What inputs? What configuration? And so forth. It makes it too complicated. In fact, it's a complicated problem, but people would like to have a single number that represents the goodness of this computer. All of those single number measures have problems, but that doesn't prevent people from using them. One of the ones which is most commonly used and most flawed is MIPS, millions of instructions per second. It's trivial computation. It's the number of instructions for a particular program divided by 1,000,000, divided by the execution time for that program. And you say that a computer is a 10 MIPS computer, say, or a 100 MIPS computer. That doesn't naturally lead you to ask the question, 10 MIPS computer on what, running what? So people are more easily satisfied with a number that represents the performance of a computer when you tell them that it's MIPS. The problem with MIPS is that it is misleading and very difficult to compare different instruction set architectures. And a computer, it's quite often the case that the MIPS and the performance of the computer can vary inversely. If I have a computer that has very complicated instructions, it will wind up executing fewer of those instructions, so then the MIPS goes down, and you might think that it's a less powerful computer. On the other hand, those instructions may be doing a lot more, so the total execution time of the program may go down. So it's not a valid measure of the performance of the computer. Yet the desire to have a single number to represent performance is so strong that people have been led to redefine MIPS. And if MIPS by itself isn't a valid number, then, well, why don't we define a relative MIPS relative to some existing machine? So you take a reference machine, which is often the VAX 11780, time the benchmark that you're interested in on that reference machine, time the benchmark on the test machine, determine what the ratio is, and then multiply by the MIPS of the reference machine. Now this is a little bit better because, in fact, if the benchmark and the test machine and the reference machine are fixed, then in fact this relative MIPS is a constant times the execution time on the test machine. The problem is that, for one thing, it becomes very difficult to even find test machines anymore. The VAX 11780 is a machine that was designed and built in the 70s, and it's even hard to find a machine anymore to run the benchmark on it. So if you need to use new benchmarks and recompute the time on the reference machines, it becomes a very difficult thing to do. Also, even the definition of a VAX 11780 as a one MIPS machine is problematical. In fact, there's some evidence that the VAX 11780 on typical benchmarks is more like a half MIPS machine. So relative MIPS, while somewhat more accurate, are still rather misleading. Again, execution time on specific programs is the best measure. Is there a domain where, in fact, a MIPS-like measurement makes any sense? Well, in an attempt to do that, people have used megaflops. The theory is that the number of floating point operations per second, megaflops are the number of floating point operations divided by 10 to the 6, divided by the execution time of the program, will vary less from computer to computer than the number of instructions per second. It's closer, but it still has the same kinds of problems. Some machines, for example, will have floating point operations that are relatively complex, like sine or exponential. And if you count that as one megaflop, or one flop to be executed, then on that machine the megaflop's rate will go down, whereas the execution time might not be increasing because it's executing fewer flops, but they're doing more. In an attempt to solve that problem, yet another patch to the kind of measurement was made, which is that instead of looking at the actual machine code executed to determine how many floating point operations are being performed, look at the original source code. And every time it does an operation which isn't a simple one, like add, subtract, compare, and multiply, although you could argue multiply is not a simple operation, you count more expensive operations with a higher weight, so that a machine that, for example, has sine built in as a single floating point operation will in fact get credit for having executed 8 floating point operations. A little bit better, but of course these numbers are fairly arbitrary. Trading off simple floating point operations for complex floating point operations depends a lot on the kind of algorithms used to implement those operations and so forth. All of these are attempts to try to patch up measures which are fundamentally flawed. But that doesn't prevent people from using them. And in fact, people tend to use even the worst possible examples of these flawed measurements. And one of the worst possible examples is peak MIPS. Rather than just looking at the average instruction per second execution rate. People will sometimes tell you the maximum instruction execution rate that this machine could ever achieve if you hand-tuned the program to show its performance off as best you can. It's basically the guaranteed not to exceed rate of the computer. It's fairly useless. It's outrageous that people actually quote that number. So if you believe me, in fact, that the only way to measure the performance of the computer is to execute real programs and measure them, what are our options? Well, the first and best option, in fact, is to use a real program that customers might use. It's hard to do because they're complex. They are complex both in their execution and the mechanics of executing them, and it's also complex to specify exactly what input and what characteristics were done so that when you execute it on a different computer, you're sure that you get exactly the same configuration and are doing a fair comparison. But in fact, there are a whole series of real programs that a consortium of computer manufacturers called SPEC have produced, and people use these quite widely to evaluate the performance of computers. In fact, there's a SPEC int, which concentrates on programs that are primarily integer calculations, and a SPEC floating point, concentrating on floating point calculations. And they're very widely read and quoted. A couple of other choices that one can make, because this is difficult to do, you could try to extract key pieces of the code where those programs spend most of their time and use those for analyzing the performance. Linpack and Livermore loops are ones that are famous. One of the problems with that is that when you're running a program which is a small kernel, you tend to artificially increase the speed of execution, for example, because you're not loading the memory system as a real program would do. Those kernels will fit into the cache of the computer and therefore execute without cache misses the way real programs would. The most amusing and interesting series of benchmarks that people have been doing these days are synthetic benchmarks that try to match the actual frequency of operations of a larger set of programs but are easier to run. They have the same kind of disadvantages that kernels do, but they have a long and checkered history. In fact, here are some of the synthetic benchmark programs that people are currently using. The naming convention is kind of interesting. There probably aren't 1 in 100 or 1,000 people who actually know why the original floating point synthetic benchmarks are called whetstones. That actually had to do with the city in which the British computer company was building a KDF-9 computer back in, I guess it was late 50s or early 60s, something like that. In fact, they had two competing compiler groups, one in Whetstone, England, doing an interpretive compiler, and one somewhere else doing an optimizing compiler. And the interpretive compiler folks produced numbers which benchmarks that were used for the performance analysis of those computers. And ever since, people have been imaginatively elaborating the names of synthetic benchmarks based on whetstones. Whetstones are concentrating on floating point operations. Dry stones concentrate on integer operations. Cornerstone, a relatively recent one, is a benchmark that tries to mix integer, floating point, and disk operations. Graphstone looks at programs that produce graphics on workstations. All of these are single process benchmarks, so they don't adequately test the performance of multiprocessor machines or multiprocess machines and measure the effect of multitasking. There's a Stanford test suite which tries, in fact, to measure that by allowing the benchmark to run with 2, 4, 8, or 16 simultaneous processors. And there are variations of that for floating point, integer, and recursive styles as well. I guess I've talked about the problems with these benchmarks. They don't load the memory system. Once they're standardized and people know that, in fact, they're going to be used to measure the performance of the machine, it's very tempting for the designers to do some special purpose optimization exactly for the benchmarks that are going to be used to measure the machine. And there's some outrageous examples, embarrassing examples, in fact, in the last several years of people who have put things into the compiler that practically recognize the existence of a benchmark that they know is going to be used, and essentially produce the result without having to do the execution because they know what the result should be. In fact, the people who do the spec benchmarks had to remove some of the programs from there because they became too easy targets for people that were, I would say, unscrupulous. I think we've talked enough about that. One of the problems in producing these measures is that you wind up measuring any of these things, execution time, megaflops, any of these performance measures on a number of different benchmark programs, and you have to consider how is it that you're going to combine the benchmark programs in order to provide a single indicator of merit for a particular computer. And there are several different ways to do these computations, and I want to describe them briefly and show you where you should use some and where you should use the others. Now, times are easy. If you have run a series of benchmarks and you have the times for execution on a particular machine or a whole series of machines, you can simply add them up. And that will give you the total running time for all of those benchmarks on that computer. If, in fact, you would like to weight those programs based on the frequency of execution that your customer might see, or that makes more sense, then you can simply do a weighted average. This is a good thing to do. It works well. If, however, what you've done is to compute rates, you've computed, even for a given set of benchmarks, the number of instructions per second or the number of megaflops per second, if you on each of the different benchmark programs, if you then take the arithmetic mean or the weighted arithmetic mean of those rates, you're going to get the wrong answer. And by the wrong answer, I mean that the machine that has the lowest average MIPS is not necessarily the machine which will have the highest average execution time. So the weighted arithmetic mean of rates will not correctly indicate the execution time of the computer. It's a bad thing to do, although there are lots of instances in the literature where people have done that. In fact, what you need to do if you're going to average rates is to use the harmonic mean. And what the harmonic mean really is a conversion of a rate back into a time in order to be able to do the averaging, and then when you're done, you convert it back into a rate. I mean, after all, the rate of execution is 1 over the time. So if you take the reciprocals of the rates, you average them using weights, just like we did for the arithmetic mean. You get, again, the average time. You take the reciprocal of that, and you get the average rate. This is the good and only way, in fact, to average rate kind of information. Now, there's a third kind of measurement you might want to make, and that is a ratio of execution time or MIPS or any of these other measures of a series of machines to one given machine, like the relative to VAX 11780 relative MIPS. It turns out that either using the weighted arithmetic mean or using a harmonic mean to measure, to combine ratios on a number of benchmarks is a bad thing to do. It gives you the wrong answer, again in the sense of not predicting what the execution time is of the computer on those programs. Now, some people have proposed that the correct mean to use in that case is the geometric mean, which is the nth root of the product of the n ratios. This, in fact, does have one advantage compared to the weighted arithmetic mean or harmonic mean, and that is that the value will be independent of the machine that you normalize to. So if you look at all the benchmarks and compare each machine to machine A, you'll get the same sequence as you would if you compared all of the benchmarks on all the machines to machine B. The problem is that it may be a consistent answer, but it's not necessarily a correct answer. You would think, actually, that this kind of computation is something that would be well understood, but in fact it's not. And as recently as the late 80s, there were a bunch of papers that were published about how it is that you combine performance measures to produce a single formula of merit for a given computer. You remember last time I showed you the book, about 40 years old, called How to Lie with Statistics? Well, this was a paper written by someone, obviously, who had read the book and tried to show how you should not lie with statistics in summarizing benchmark results. And in fact, this was the paper that recommended that for normalized measures, like relative MIPS, you use the geometric mean, because in fact it's the only mean that is independent of the machine you're normalizing to. This paper, in fact, produced a whole series of follow-on papers and sort of shouting matches in these esteemed academic journals about whether or not that's the right thing to do or not. One of the subsequent papers said, for example, the geometric mean does provide a consistent measure in this context, but it is consistently wrong. In fact, it doesn't predict execution time. So the answer is that you should probably not even use geometric mean for normalized measures. The best thing to do is, in fact, not try to combine things like normalized measures at all. What you should do is go back to the original measurements, the execution time measurements, combine them according to whatever weighting you choose and you think is appropriate, then compute the normalized measures. Now, the geometric mean is not a totally useless computation. In fact, there are a couple of places where it is very useful. One of those places is wherever there's a kind of compound growth calculation to be done. So if you're interested in computing, for example, the average improvement of a computer when in 3 separate years, let's say 1991, 1992, and 1993, the improvements were, I don't know, 25%, 20%, and 15%. The computation to be done in that case is, in fact, a geometric mean. It's the cube root of 1.25, the improvement for 25%, times 1.2 times 1.15. I hope that's readable. Probably not. That, in fact, to compute the average improvement of a compound growth, you need to compute the nth root of the product of the individual improvements. So geometric mean is occasionally useful. You just have to be careful and use it in the right places. Questions, comments? We've talked about performance and how to measure it. The other part of the cost-performance equation is cost. And although it would be nice to be able to do it, you rarely get the opportunity to ignore cost as part of the design criteria. There are a couple of issues that you ought to consider. One, and I think we alluded to this before, is that just as in measuring performance, predicting performance based on the time your machine will ship and not the time that you're beginning the design, you have to base projected costs on the costs at the time the machine will ship rather than the time you're doing the design. And those change a lot. The costs will change because as technology improves, people learn how to produce for lower cost. One of the things you need to consider is that the packaging has a huge effect on the cost of design. And if you can do anything to avoid crossing a package boundary, then you've saved an enormous amount of of dollars in the eventual cost of the machine. Yeah.
Define packaging.
Say again?
Could you define
By,
packaging?
by packaging, there are several components to packaging, but the one I was alluding to mostly here is the ability to include as much logic and functionality of the machine as you can on a single chip. If you've got to split to a second chip, and we'll see some of these cost numbers later, the cost of taking the same logic and dividing it into two parts and putting it on two separate chips is extremely high, both in the cost and in the performance of the resulting computer. I think these things are fairly obvious. One interesting thing to consider is that in looking at future costs, you have to consider, because of the learning curve, which part of the curve you're on. If you're designing a computer, let's say at the beginning of 1994, you might look at the cost of memory and decide that 4 megabit RAMs are $13 per 4 megabits, so that the cost per megabit is 3 or 3.5, and the cost for 16 megabit RAMs is $4 or $4.5 per megabit. But the cost for 4 megabit RAMs is not going to change very much over their lifetime, because they've already gained the advantage of the cost reduction as part of the learning curve. The 16 megabit RAMs are going to reduce in cost a lot faster. So in designing your computer here for eventual production here, you've got to predict that the technology to use is the higher density, even though at the time of design it's more expensive. Some of this takes some use of crystal ball. Let's look a little bit at the costs of producing ICs. The cost of an IC can be represented as the sum of several factors. One is the cost of the die itself. The die may or may not work, so there's a cost in doing testing of that die, and then the cost of packaging the die. Having produced the die, tested it, and packaged it, in fact, it may be a non-functioning component, so you have to divide that by the yield, the number of the fraction of dies that have to be thrown out because they don't work. The cost of the die itself is the cost of a wafer. I'm sure you've all seen the mostly circular wafers that dies are produced on, divided by the number of dies you can fit in the wafer times the die yield, the number of dies that are good. The cost of the wafer, well, rather the dies per wafer, are geometrically computed based on the number that you can fit into a circular die. If you compute the area of the total die, divide by the area, the area of the total wafer, divide by the area of the die, you get a first approximation to the number of dies on the wafer. Because the dies are rectangular and the wafers are circular, you have to reduce that by, roughly speaking, the amount of dies that are on the periphery of the wafer. So this is the circumference divided by the hypotenuse, so to speak, of the wafer. This is all an approximation. And then on the wafer as well, there are bunches of test dies that are used to monitor the process which produces the die. Let's get a feel for what typical numbers are in producing ICs. 8-inch wafers are the state of the art these days, and they're very expensive. A single wafer costs on the order of $2,000 or $3,000. And the number of dies it holds obviously depends a lot on the size of the die. If it's a PowerPC class die at about a centimeter squared, then there are 269 of them per wafer. But if it's a Pentium class machine where the area of each die is 3 square centimeters, then there are only 79 of them. So the incentive to keep the die size small is extremely high. Let's look a little closer at how one might calculate the yield based on defects in the wafers. Yeah.
On the cost of the die formula, it says on the cost of wafer over dies per wafer times die yield. But on the dies per wafer, we already subtract the test dies. So aren't they affecting the cost twice? I mean,
No, those are two different things. Die yield accounts for the number of dies that might be good but happen to be broken. They don't work. And test dies per wafer are dies that are put there explicitly to test to see whether the process is working right. And they could never have been used because they're not designed to be functional chips. There's a whole sub-industry involved in trying to predict what the yield of dies are, the fraction of those dies that actually work and meet spec. This is a model which I don't intend to derive and is partly based on probabilistic analysis and partly based on empirical evidence that just tries to give you a feeling for what it depends on. And the interesting part here is that obviously the die yield is proportional to the wafer yield. It also is proportional clearly to the number of defects per unit area in the wafer. The bigger your die, the higher the likelihood that your die is going to land on top of a defect. But defects are not necessarily uniformly distributed across dies. They tend to be clustered, and it tends to depend a lot on the complexity of the process that produces the ICs. So in fact, the die yield tends to be inversely proportional to some power of the area of the die. And that power depends on the process. It can be as bad as something like 3 for complicated by CMOS processes. The moral is that the die cost could be as bad as proportional to the cube of the die size. If you, well, you know what that means. Which makes the incentive to try to keep the die size low for low performance, for low cost chips extremely important. Let's look at some typical examples or numbers. Again, for a 20 centimeter wafer, the yield on the wafer itself might be 90%. There might be 2 defects per centimeter, and let's say that we're trying to produce a 1 centimeter square die. That produces a die yield, and I think this was done with the easy case of alpha equals 2, produces a die yield of 22.5%, which is actually quite outstanding. I mean, it means that in this industry, you throw away 3/4 of everything you make because it doesn't work. But still, that leaves enough profit margin for people to make these things productively. If there were 269 dies per wafer, in the case of the PowerPC class machine, then in fact this represents a cost of about $33 per correct die, per working die. If you double the die size from 1 centimeter to 2 centimeters, then the yield has gone down to 10%. The cost per die has gone up to $167 per die. Now the other thing to remember, like the example I showed for RAM costs, is that if it's a new process where the learning curve has just begun, then in fact you may be able to survive a very costly die price in the beginning, because later in the life cycle of that particular process, the cost will be coming down quickly. If you're using an existing process, then chances are it's not going to be coming down very much, and you'll have to live with that cost for quite a while. The cost of producing the IC is not the only cost in producing the computer, obviously. Packaging and testing is significant. For complex chips, it could cost as much as $10 or $20 to chip just to see that the packaged chip, even if the die tested correctly, is a functioning packaged chip. Once you've got ICs that work, the other kind of depressing thing is that the total system cost includes only a small part for the non-memory IC components. People have estimated that 10 to 20% of the total system cost for a workstation, say, represents the non-memory ICs, the CPU, floating point unit, memory management unit, caches, and so forth. That memory, 100 megabytes of memory that a good workstation ought to have these days, probably 40 to 50% of the cost. And the rest of the cost goes into I/O interfaces, devices, cabinets, power supplies, all the rest of the stuff. And if you think that's bad, then in fact the price charged to the consumer eventually includes lots of other components. In fact, probably 4 times as much cost of things that have absolutely nothing to do with the cost of production of the computer itself. It's selling costs and overhead for G&A and research and development, which is in fact your salary, assuming that you're a computer designer and computer engineer, and somewhere in there the company actually wants to make some profit. So it's not at all surprising for a company to look at the cost of production of a computer and say that in order to be able to make money selling that computer, they have to multiply that by a large factor, 3, 4, 5, or even 6, before they can sell it and make enough money to cover all of these other costs. I don't know if somewhere in Stanford somebody teaches a course on the economics of building computers, but actually it's a fairly interesting topic. Let's look, before we wrap up here, at some examples of numbers representing cost and performance for microprocessors that are still in production. This information is often very hard to come by. In fact, a lot of these numbers, you might want to focus in on this top part here, a lot of these numbers are guesstimates based on some published information and some clever people who think they understand what the yields are in the semiconductor manufacturers. That's information which they jealously guard because they view it as highly competitive information. Over on the left here we have machines which are ancient, that have been in production for a very long time, and they are incredibly inexpensive. The 6502 is the machine that the Apple II was built out of, and in fact it's a tiny chip. It's a 7mm square chip. The yield these days is 99%. It's at the point where they don't even bother testing them. They just build them, package them, and do the final test either with the packaged IC or after it's installed in a system. The cost for a good die is about 40 cents. The cost of the package is half that, is 20 cents. So a third of the cost of the assembly is just in the package. But the entire chip sells for, or can sell for under $1. At least the cost of manufacturing is under $1. What it sells for depends on how much they need to multiply by in order to cover the other expenses. A couple of other things that are interesting in a chart like this. One is that 2 implementations of the same machine may differ a lot. These are 2 implementations of the Intel Pentium, one in 0.8 micron by CMOS, one in 0.5 micron by CMOS. The cost is about a factor of 2 different, primarily because of the decrease in die area. Die area has gone down from almost 300 square millimeters to 163 square millimeters. And even though the wafer cost size has gone up, the die size has gone down to the point where the yield goes up from 25% to 32%. So the cost is now almost half the cost in the older technology. Other interesting things to look at are the incredible costs of packages when the pin size gets very high. If you look at the RISC 4000 series, for example, the cost of a good die is about $38, but it's a 447-pin grid array package. The cost of the package is more than the cost of the die. It's about $50. So in designing these computer implementations, you really need to think hard about the packaging that your design implies and what the cost implications of that are. I think we'll stop there. You can amuse yourself with this chart at your leisure. We've come to the end of cost and performance. Next week we'll actually start getting into instruction set architectures, evaluating them, looking at the alternatives, and looking at real examples. David.
One other thing, even though Monday is a holiday, we'll still be having office hours Monday night. So since you've got a problem set due on well, shortly thereafter, I'll be around.
Thank you.